Today, I want to talk about the difference between analog and digital electronics. We're all familiar with an analog clock. There's a minute hand and an hour hand. And we're familiar with the digital equivalent. And we're also familiar with the Morse code, or at least we know a little bit of it. We've heard about it. That it's a way of signaling information where you have a dot, dash, dot, dash, dash, dot. Now this is a way of transmitting information that's very similar to how a computer or how a digital computer transmits information. The digital computer uses, instead of dots and dashes, it uses zeros and ones. For example, this dot may correspond to a 0. This dash correspond to a 1, 0, 1, 1, 0. But what does this mean electrically, a 0 and a 1? Let's presume we have two metal plates. And we'll put a positive charge on the top plate and a negative charge on the bottom plate. This will produce an electric field between the two plates. And we can call this condition a logical 1. We have a potential difference. We have a voltage difference between these two plates. Now if I put a resistor between the top plate and the bottom plate, the charge will redistribute and it will become something like this, where the top plate has equal plus, minus, and the bottom plate is plus, minus. In this case, there's no electric field because both plates have the same voltage or the same electrical potential. So we can call this condition a logical 0. Let's consider another analog and digital example. Let's consider a thermometer. Here I have an analog thermometer, and with this thermometer I want to measure the temperature of water. If the reading of the thermometer is down here, the water is freezing. It's 0 degrees centigrade. If the thermometer reads up here, we'll say this is 100 degrees centigrade. So at the top the water is boiling, at the bottom the water's freezing. I want to represent this analog thermometer digitally. So let's consider how I could do this. For example, I could set up a digital scale. And let's consider one bit of digital data. For example, I'm going to try and represent this thermometer with just one bit of digital data. I'm going to draw the midpoint at about 50 degrees centigrade. And if I have a digital 1, I can say I'm in this region of the thermometer. If I have a digital 0, I'm in this region. But this is not a very accurate thermometer. It just tells, am I in the cold zone? If it's a 0, I'm in a hot zone. If it's a 1. So 1 bit isn't going to make a very good digital thermometer. So I want to add another bit. So I can set this scale more accurately. In this case, rather than just 2 zones, with 2 bits, I can have 4 zones of temperature. For example, this zone I can represent by a 0 and a 0. This could be a 1 and a 0 and a 1, and all 1s up here. So I've improved the accuracy of my thermometer, but it's still not very good. So I could add another bit of data. And every time I do that, I double the resolution of my thermometer. For example, this could be 3 zeros. This could be 1, 0, 0, and so on, etc. So with 3 bits of data, I can have 8 different states. But let's presume I really want a better thermometer. So I'm going to have 8 bits of data. 1, 2, 3, 4, 5, 6, 7, 8. And now I can get a very fine resolution. In fact, with 8 bits of data, I can get 2 times the 2 raised to the 8th power, which is 256 resolutions. With 3 bits of data, it's 2 to the cube, which is 8 different states. And with 2 bits, it's 2 raised to the 2nd power, which is 4 states. And with 1 bit, it's 2 raised to the 1st power, which is this 2 states of data. So the more digital bits of data, the more accurate digital thermometer I can make.